All right, welcome back. So last time we looked at an example where we went through like heavily with plotting points to kind of help us get a feeling for what the curve looked like. And we actually get this shape here. And this is again a shape of what's called a cardioid. This cardioid shape, kind of a heart shape. So we're going to look at a couple that are a little easier. The first one is r equals a. So where we are, in other words, the radius is given as some number, like r equals 2, or r equals negative 2, or negative 1. Okay. Well, what happens then is the radius is fixed, and the angle can be anything it wants. So it turns out what you end up getting is a circle, just a simple circle centered at the origin, if r is equal to a constant. It's just a circle centered at the origin. With a radius that is absolute value of a. So if a is a positive number, of course, you would have that number, and you'd actually start as theta goes from 0 onward. You would start here, and you would make your way around the circle. If, on the other hand, r was negative, then you'd still be starting with a theta facing this way, but because of the negative, you'd actually start over here, and you'd be going around the circle as well. Right? But in either case, you end up getting a circle. You'll end up getting a circle if r is a constant. If, on the other hand, theta is equal to some constant, so here theta equals b, where again b is a constant. So now the theta is fixed, and the radius is allowed to vary as much as it wants. So if I draw in here my positive x-axis, then you're heading at some angle b with respect to it. All right, where b again is some angle in radians. And you can go in either direction, extending the radius as far as you want. Right. And you can go forward with positive radius, but r can be anything at once, so it can also be negative. So we can go anywhere that way. And so we end up getting a straight line that passes through the origin. We end up getting a straight line that passes through the origin. Now, let's go back to this equation that we looked at, r equals cosine theta plus 1. And one of the things we're asked to do is to convert from r theta form over to xy form. So let's consider that as a problem. I'm going to write the equation r equals cosine theta plus 1 in xy coordinates, or in other words, in rectangular form. Okay. So the idea here to go from r theta form over to xy form is xy form, remember, is based on this idea. If I have an r squared, I can replace that with x squared plus y squared. If I have an r cosine, I can replace that with an x. If I have an r sine, I can replace that with y. So those are kind of the ideas here. That we're looking at here. So those are the ideas that we are looking at here, is that x can be, r cosine theta can be replaced with an x, and r sine theta can be replaced with a y. And if we have an r squared, I can replace it with x squared plus y squared. Okay. And so here we can accomplish our goal by saying, okay, I need to get things like r cosine theta. So what I actually decide to do here to kind of get to that is I decide let's multiply the whole equation by r on both sides. So on the left-hand side, that would give me an r times r would be r squared equals r cosine theta plus r times 1. Now, r squared can be replaced as x squared plus y squared. R cosine theta can be replaced by x. Now remember, r squared is equal to x squared plus y squared, so r could actually be either plus or minus the square root of x squared plus y squared. Okay, so let's take a look at this. This is a very ugly, complicated xy equation. Let's just go ahead real quickly and take a look at its graph on Desmos. This is not something you would want to ever try graphing by hand. So we have x squared plus y squared equals x and then plus square root of x squared plus y squared. And you can see that I actually don't need to bother with the plus or minus because I do actually get the full graph. In fact, I don't have to worry about the minus here because in the equation r equals cosine theta plus 1, I actually was always positive. So we can actually drop off the plus or minus idea in this example, though sometimes you would have to include it. But in this case, that thing is never negative, so we can just take the positive root. And you can see we do get the whole graph. A pretty messy, complicated thing in xy form. Not so much so in r theta form. As another example, let's consider the equation here. R equals a sine theta. Okay, or r equals a cosine theta. Right, so just a constant times either the sine or cosine. Well, once again, we can multiply both sides by r, right, in both cases, to bring in the r form. So we get r squared equals a r sine theta, or over here, r squared equals a r cosine theta. And simplifying, we would get x squared plus y squared equals a times y. And over here, we would get x squared plus y squared equals a times x. And it turns out equations of this format in xy form are actually just circles. If you were to go through the trouble here, like for example, if a was equal to, say, 2, you could bring that over, and you'd actually find out that this is a circle. You'd have to complete the square to graph it, but these actually would both be circles. So using this idea of trying to manipulate the equations, some r theta equations can be turned into xy equations. And again, some of those xy equations might be a little easier to work with than others.